So again, silly diagram that they use in every chapter, talking about the 4 parts of the textbook and how they divide things up. We're going to talk first about tables. There are 2 kinds of tables in ArcGIS. Feature attribute tables of feature classes. Every feature has a record with attribute values. And there's data tables with geocodes, such as census tract IDs. And you can add a table to ArcGIS Pro as well. And you can join that table to feature classes to add more attributes to those features. And you can join via the same geocode values in both data tables and feature class attribute tables. Census data example, too many census variables to supply already in the feature attribute table, so download the custom table and join the appropriate polygon feature class. Alright, so how external table file formats, let's talk about those a little bit. The most basic is a plain ASCII2 text with comma separated values, or a CSV file. These are very transportable as the formats go. They're also very large files. Each table record is a row terminated with a line break character. It's invisible, it's a non-printing value. It has values separated by a delimiter. It's often a comma, telling it when one thing is done and when to go to the next. For data values that contain the delimiter, enclose the value in double quotes. And sometimes columns get the wrong data type or input, and use double quotes to force text data types for digits, say for house numbers and things like that. Then there's, of course, there's old standby, the Excel type files, or XLS or XLSX files. Excel 2003, you can have up to 65,000 rows and 256 columns. 2007 and later, you can have 1,048,576 rows and 16,384 columns. There's also a database table, or DBase database table, or DBF file. This is a legacy format. Field names can only be 10 characters long. ArcGIS Pro tends to truncate the field name to the first 10 characters. It has a maximum of 255 columns, and you can open these in Excel, but you can't save the DBase file formats from Excel anymore. One time you could, but with the last updates to Excel, because this is a really old legacy style database structure, Excel no longer supports that function. And then there's Microsoft Access databases, or MDB files. These can be up to 2 gigabytes in size, and you can see other limits as well. If you're interested, you can check out this web link to find out more. So that's the basic data table format. Well, they're kind of rectangular with one value per cell. You have columns, which tend to be fields. Those are your attributes, and then your individual rows are your records or your observations. Same basic format as ArcGIS Desktop, same format you have in ArcGIS Pro. The first row must have column names that should be self-documenting. So when you look at that first row across the top, the individual rows should tell you what that column is: shape, geoid, pop total, etc. The first character of an attribute name must be a letter. You cannot start a column with a number. The remaining can be any letters, digits, or underscore characters, but you cannot use blanks, periods, or special characters. No dollar signs or exclamation points. Standard ArcGIS Esri related file type rules: letters, numbers, and underscores only, please. All additional rows of data table must contain only attribute values, in other words, raw data. None of the rows can be sums, averages, or other statistics for rows. So, for example, if you had male bikers and female bikers, and you had total bikers, and you calculated that row, or I'm sorry, that column with some sort of a math function where it combined the two together, you couldn't do that. It just won't work. You have to have just a number in the box. Each table has a primary key attribute with 2 properties. Each value is unique, and there are no null values. This is typically referred to as the object ID. It is the identifier which tells you that this is a distinct row or input in the dataset. Okay, now that we've covered what the basics of tables look like, let's talk a little bit about geocodes and what they are. Geocodes are based loosely, more or less, off of the FIPS codes. These are the Federal Information Processing Standards. That's what FIPS stands for. They were developed by the National Institute of Standards and Technology, and they're codes for place names throughout the world. The ANSI codes 2010 basically replaced FIPS, the American National Standard Institute code. And so it's kind of, like I said, it replaces FIPS codes. It's for counties, states, provinces, countries, states, provinces, counties, metropolitan statistical areas, cities, and places, such as Indian reservations, airports, and post offices in the U.S. So how does an ANSI code work? Well, they follow political boundaries. So the country would be the U.S., the state would be, for example, 42, which is Pennsylvania. The county would be Allegheny, which would be 003. The minor civil division, which is Pittsburgh, would look like this: 42,003,61000. Now, when we look at these political boundary features, you can see how that would look. The U.S., Pittsburgh, Allegheny County. Going from the top left counterclockwise. Top left is the U.S. Going to the top right, we have Pennsylvania. Going to the bottom left, we have Allegheny County. And then going to the bottom right, we have that unique statistical area of Pittsburgh. So how does that work with these statistical boundaries? If we look at it a little bit further, we can have census tracts and census block groups. So, for example, the tract would be 0201, and the block group would be 002. And so you notice the numbers here in the code was US 42003, 0201, 002. And then here we have census tract, the census block group. And you can see how those numbers relate to the ANSI codes. Other geocode examples are U.S. postal codes or zip codes. There's also congressional districts, school districts, local government, cadastral data, block and lot numbers, for example. Cadastral data are legal boundaries that are organized as such. Parcel ID numbers would be something like within a particular city. You might have a parcel, a block and lot, or a PIN number. 125th Avenue, Pittsburgh, might have that particular number associated with it. And there you go. See the PIN number, and that associates to the parcel, the block, and the lot. Okay, so this is GIS lecture for week 4, or lecture 4, on file geodatabases. And what I'm going to do is go through the PowerPoint slides like I normally post on Blackboard, but these will have narration included. I will also take that set of narrated slides and convert them into a video file, which I will upload to YouTube, to my YouTube channel, and provide you with a link so you can access it should you be somewhere or on some device, like for example a netbook or a tablet that doesn't have PowerPoint, and you still want to take in this riveting lecture. You'll be able to do so via YouTube. XY data. Data tables include XY attributes like latitude and longitude. These are common GPS data that you will see sometimes in tables as well. And you can take data like that and go to display XY data, and it will simply ask you which is the X column, and you tell it, and which is the Y column, and you tell it, and it can then relatively quickly post those up by identifying longitude as X, latitude as Y, and then identifying a spatial reference. In other words, you have to tell it what projection it's in, and it can then display that data. How do you export this as a feature class? Well, once you display it, you can go through the process of doing that as well, using geoprocessing to copy the features. Next, we're going to look at the U.S. Census Bureau's geospatial data. The U.S. Census Bureau started building a map infrastructure in the late 70s and early 80s. The census mapping needs were twofold. They needed to assign census employees to areas of responsibility covering the entire country and its possession. To report and display census tabulations by area, officials determined that the smallest area needed for these purposes is a city block or its equivalent. So one person assigned to a city block, and then we look at other areas where the people are less dense. We had to pick a similar number of people, a similar size population, but it might not be the same size area. So we ended up with something called the tagger files, the topologically integrated geographic encoding and referencing files. These are available for the entire United States and its possessions. They're comprehensive in details. Includes the following geographic features. So the tagger census data has roads and street center lines, all the railroads, the rivers, the lakes, and all the census statistical boundaries. So here we're looking at the tagger census tracts. The statistical boundaries below are the county, minor civil division levels. Generally between 1,000 and 8,000 people is what we're looking at. That's typically about 1,700 houses and units, or about 4,000 people. And these groups, these tracts, should be homogeneous in terms of their population. In other words, they look for clusters of people that are of similar economic status and living conditions. They don't throw in a really rich neighborhood and a really poor neighborhood beside it and combine them together. They should try to make these groups as unique and as much like and representative of the entire population of the tract as possible. Normally, normal boundaries follow visible features. They may follow governmental units and boundaries and other non-visible features. So what that means is it can stop at the edges of roads. It can go to the boundaries of rivers. It can also stop at things like county lines that you can't see. They try to take use of all these features to divide the groups up into these units that make sense. So census blocks. Okay, blocks are a subdivision of a census tract. We've already talked about what the census tracts are. Now imagine 400 housing units with a minimum of 250 and a maximum of 550. So you divide up each census tract into blocks, and each block has between 250 and 550 houses. And these tend to follow clear visible features such as roads, rivers, and railroads. These do not necessarily follow those political boundaries, because if a political boundary occurs, it would have been in place in the census tract, and so the block wouldn't necessarily be intercepted by it, because blocks are parts of tracts. Census blocks are the smallest areas for which the Census Bureau collects and tabulates the decennial census information. Block boundaries, visible streets, streams, roads, etc., invisible, are also included in this. There's limited data and attributes that are available. So what kind of data is available from the U.S. Census Bureau? That's a really good question. Well, first let's look at the decennial census data. Decennial meaning, I guess every 10 years or 20 years. Yeah, I think it's 10 years. The summary file, or the summary file 1, or SF1, is basically the short form. It has 100% of the population data, and this is available for 1990, 2000, 2010, etc. And what this data includes is population, age, sex, race, families, households, and housing units. Now, we also have tracts, block groups, and blocks. When we look at the summary file 3, or SF3, this is from the year 2000 and earlier. It's the long form. So basically 1 in every 6 households are randomly selected to collect more detailed information. Things like income and poverty, educational attainment, citizenship, employment, workplace, disability, transportation, travel time to work, detailed housing attributes such as housing value, etc. Languages spoken, and ancestry. And you can see that this is at tracts and blocks group level. The American Community Survey was started in 2005. This replaces the decennial long form of the SF3 census questionnaire. They randomly select about 3 million addresses each year to participate. They use the master address file, or the MAF. This is accurate, up-to-date inventory of all known living quarters and places of employment in the United States, Puerto Rico, and associate island areas. It has a rolling 1, 3, and 5-year estimate and a 90% confidence interval. Add and subtract the margin of error from the estimates to get the confidence interval. Basically what they're doing is they're randomly selecting a certain number of people every year and doing a continually updated estimate of all these values, so you get it in a much more timely fashion. But it's not an absolute count. It's not a true census, because it is an estimate, because they only survey a percentage of the population. So there's some margin for error, hence the 90% confidence. So what are we looking at? The ACS estimates. The data is pulled to produce 1-year estimates. Data published for areas with populations of 65,000 or more. It's not available for tracts or block groups. The 3-year estimate goes down to populations of 20,000 or more. It's not available for census tracts or block groups. Then they have the 5-year estimates. This is population of almost any size, and it is available for tracts and block groups. And with a 5-year estimate, that means that they've got more data that they've collected, and they're more confident in what you're looking at. So what are the survey questions? Age, sex, race, family and relationships, income and benefits, health insurance and education, veteran status, disabilities, where you work and how you get there, where you live, and how much you pay for certain essential costs. What are some of the other census features? Well, there's a lot of geographies that they deal with. When you go to the Census Tagger Products website, this is the address according to the textbook. It can be difficult to find this section. This section is important because this is where all the spatial data is found. Almost everything else the census has is in tabular format. And a lot of times students will make the mistake of thinking they have the data that they want, only to find out that they've got the tabular data they want, but not the spatial data that goes with it. And as you can see under Tagger Products, there's various links. The Taggerline shapefiles, there's a Taggerline geodatabase, and there's selected demographics and boundaries and cartographic boundaries in the Tagger web, and there's all kinds of stuff. And so much of what you need is here, and this is going to be the page where if you're looking for census data, you need to start. So when we look at cartographic boundary files, these generalized boundary files clip to a simplified version. They're used for small-scale thematic maps. The KML, or cartographic boundary file, this is census. This is counties and census tracts, and they operate off of a geographic identifier, or a GOID. This would be available for like the 2010 census. The Tagger web has linear features like roads and highways and streets and railroads and other single line type things, and then area waters for rivers, lakes, and glaciers. Shapefiles tends to be an older Esri legacy format that has been replaced with features in geodatabases, but there's still a lot of data that's out there and available in this format. I want to talk briefly about joining tables. So to join tables, you basically just take two tables and put it together on the fly to make one table. That's a basic one-to-one join or a one-to-many join. You can do this with feature attribute tables, data tables, as long as they have the same sort of geocode. So what does that mean? Here's an example. We have the Maricopa County, Arizona tracts feature attribute table, and below that we have population and per capita income data table. And the thing that I want to point out here is that both of these have a GOID 10 file. Turns out this is a pretty good candidate for a join. The problem is different field types. One is numeric, one is text. The solution is to create a new numeric field and calculate values from the text field. And basically you can join tables, right click the tracks layer, join and relates, and then click the add join. You can classify per capita income field. Values will only appear with numbers. Your values will appear with the number fields, and then boom, all the data that you had from the census is now attached to the other data, and it shows up. Spatial joins are similar, but it's not quite the same thing as a tabular join. Spatial joins join features using not an attribute field, but their physical location. It enables data aggregation, counting or summing points by polygons, for example. And it also allows you to do things like common spatial joins, like points to polygon for counts, polygons to point for things like adding text, and points to point to create things like distance files. So how does that look? Points to polygon join, drug offenses by neighborhood. You start with the crimes, which would be the points, and the neighborhood would be the polygons. The point to polygons and the geoprocessing spatial joins. Tell it what you want to do, fill in the boxes, and boom. It will take your data, and now you have the neighborhoods with the counts from the joins, which you know to be the number of drug offenses, and you can see which counties have the most. Polygons to points would be neighborhood name with each crime point. So now, not only do you just have the crime data, you also have the name of the neighborhood where the crime occurred, because maybe that's the way you want to analyze it. Points to points, how close is a crime to a school? So you start out with crime, points, and school that are points. Now what do you do next? Well, you go through the process and you're going to match them up, and you want to match the closest. So you're going to find which school is the closest to the offenses. And once you've done this, now when you have a drug violation, you'll know which school it was closest to. Okay, well, that's about it, folks. What we've covered tonight talks about some of the basic ways that we store data and we move data around relative to tables and feature classes and whatnot. We've also talked a little bit about how and where you can get census data and how powerful it is, and how it's geocoded out so that you can figure out what the data means and where it's from and what you can do with it and how you can understand the codes to figure things out. We've also looked at some of the really basic tenets of modeling in GIS, which is the ability to spatially join features and the ability to join attributes and tables of additional information together based on common unique identifiers. And these are all seemingly basic tricks, but it turns out that prior to the advent of GIS, these were really difficult things to accomplish, but now in the geographic information system environment, we can not only do these things, but we can do these things to leverage data and information into real, useful, powerful knowledge. And that's what GIS is all about. So, take some time, listen to this once or twice, read your chapter, and do your exercises and things that you're assigned, and good luck with your exam. And we'll see you next week, assuming we all don't get flooded away. Goodbye.